Hi, this is the first in a series of videos intended to make your AP Calculus class a little bit easier. We're going to begin with the topic of implicit differentiation, moving from kind of basic ideas at the beginning through a little bit more sophisticated as we go. Let's read the problem first. Consider the implicit relation defined by, and here's our equation. We're supposed to first find the first derivative. Now, if you don't know how to do implicit differentiation, you act like it's a normal function, except that the chain rule applies whenever there's a y. So this thing right here, we can differentiate like normal, but the 4y squared is going to have a bit of an issue because there's going to be an outside function, which is the squared part, but then an inside function, which is what the y is. You may already know this, in which case this is going to go kind of quickly. So number one, we would get 18x, that is the derivative of 9x squared, plus, use the power rule first to get 8y, but then because of the chain rule, you must multiply by y prime. At all points during this problem and any others that you do with implicit differentiation, it's better to write y prime than dy dx because it takes up less space and you end up writing it over and over, so you may as well use the quicker version. So 8y times y prime. On the other side, you get 0 because that's the derivative of any constant. The task now is to isolate the y prime. So we need to isolate that, get it by itself. We'll begin by moving the 18x to the other side. If you're in a calculus class, it means you can do algebra quickly, so I'm going to move fast here. Now, y prime is negative 18x over 8y. This can be reduced so that y prime will be negative 9x over 4y. This is the answer to the first question. Find the first derivative. Now, the subsequent questions obviously are going to make use of this, so we'll need to refer back to this formula. First of all, number two, verify that the points 0, plus or minus 3 lie on the curve for the relation, and that for these values, the relation has horizontal tangent lines. This does have two parts. First of all, we need to verify that those points lie on the curve in the first place. So for problem 2, checking that 0, plus or minus 3 actually lies on the relation it's a matter of replacing x with 0 and replacing y with 3 or with negative 3. Ordinarily, we would need to test the 3 and the negative 3 separately. But in this case, we luck out because the y is squared, and so we'll have the same result. That means that we can just plug in like plus or minus 3 at the same time, and we'll verify both. So we'll set x equal to 0 and y equal to plus or minus 3. That will give us 9 times 0 squared plus 4 times plus or minus 3 squared equals 36. If this equation is true, then we're in good shape. That means that this actually does lie on the relation. Obviously, the beginning is 0 because 9 times 0 is 0. 4 times either 3 or negative 3 when you square it becomes 9, and this is equal to 36. So the points do lie on the relation. So we have done this part, verify that the points lie on the curve for the relation. Yes, now we need to do the second part. For these values, the relation has horizontal tangent lines. Horizontal tangent lines consist of a single condition. Do you know what it is? It means that y prime equals, that's the slope of the tangent line, right? That's what y prime represents. In order to have a horizontal line, you must have a 0 derivative. So y prime equals 0 is the thing we're testing here. we have a formula for y prime. It is negative 9x over 4y. So at 0, comma, plus or minus 3, y prime will be equal to negative 9 times 0 over, well, again, we kind of luck out because ordinarily we would need to test it twice, but the top of the fraction is 0 in both cases. So the top will be 0, and so it doesn't really matter what the bottom is. The whole thing ends up being 0. So since y prime equals 0, the tangent lines are horizontal. Okay, but now we have a follow-up question. Verify that another couple of points, this is number 3, lie on the curve, number 3, and that for these values, the relation has vertical tangent lines. Verifying that plus or minus 2 comma 0 lie on the curve, that's the same process, but now in order for it to have vertical tangent lines, we'll need to do something a little different. We'll do that when it comes to it though. Numero tres, to plug in plus or minus 2 comma 0. We use the fact that this is the x and this is the y. We can do the same thing that we did before. We can cheat and do both at once. 9 times either plus or minus 2 squared plus 4 times 0 squared. Is this equal to 36? That's the question. Well, plus or minus 2, square either of them and you get 4. So 9 times 4 equals, 4 times 0 is 0, so that goes away, equals 36. And it is true, so yes, plus or minus 2 comma 0 lie on the relation. Now we need to verify that at those points we have vertical tangent lines. Well, horizontal tangent lines meant that we were looking for the derivative to be equal to 0. What does a vertical tangent line mean? You know this. Yes, it means that you want the derivative to be undefined because think about it. The derivative represents the slope, right? Slopes, that's what a derivative is. If the slope is vertical, then the derivative should involve division by 0. So a vertical tangent means that y prime is undefined, and specifically it divides by 0. It's not hard to see that division by 0 requires that y equals 0, right? Look at the formula for y prime that we have from before. If y gets replaced by 0, then this will result in division by 0 because the bottom of the fraction will be 0. To get more explicit about it, we can say y prime equals negative 9 times, yes, plus or minus 2, then divided by 4 times 0. It doesn't matter what the top is because the bottom is 0. So these are both vertical because y prime involves division by 0. So we are conquering this problem like crazy. Okay, number 4. In the first and second quadrants, the relation is concave down. In the third and fourth, it is concave up. Verify this. All right. This doesn't tell you that it involves the second derivative, but by this point in the class, anytime you hear the words concave down or concave up, you should automatically think, bingo, this is a second derivative thing, okay? Very brief review of this. Think about, this is number 4. First of all, concave down looks like this. So what concave down means is that the second derivative is negative. So y double prime is negative. But why? Why does it mean that? Think about the second derivative as being the derivative of the derivative. And now I'll use rate of change instead. It is the rate of change of the derivative. It's how the derivative is changing over time. Think about a bunch of tangent lines to this shape. Are these lines becoming more positively sloped over time or more negatively sloped over time? You've got a nice big positive slope here, a smaller positive slope here, and now they're actually turning negative. So the reason that this is the shape of a concave down graph is that tangent lines become increasingly negative. Now that means that the rate of change of the derivative must be negative, right? So the rate of change of the derivative being negative means that the tangent lines become more negatively sloped over time. For the exact reason flipped over, the same reason flipped over, concave up, which looks like this is going to have tangent lines that start out highly negatively sloped, but over time become more positively sloped. I'm just drawing one side of these tangent lines, by the way, because it makes it more clear what's going on. But really, this tangent line would continue on both sides. But this just makes it clearer, like what's actually going on. This starts out really negative, but then less negative, positive, more positive. This means that the tangent lines become increasingly what? Increasingly positive, right? So the tangent lines are increasingly positive, and so this means that the derivative of the derivative is greater than 0. Now, sometimes we don't have to answer this question for this problem, but sometimes you do have a question of whether a tangent line provides an overestimate or an underestimate for a function. If you look at this, you'll notice that concave down functions have tangent lines that lie above them, right? All of these ones, if we were to continue drawing them on both sides, they would have the curve underneath and the line on top. Okay, well, that means that a concave down function is precisely the sort of thing for which a tangent line provides an overestimate. Because if you zoom way in here, then check this out. Say that I go close to this point by walking just along this line a little bit. Well, I use the line to approximate the value of the curve. But the line is above the curve because the curve is concave down. So nearby, this will provide an overestimate. But for the same reason in reverse, near a point of tangency, a concave up function will have a linearization or a tangent line that provides an underestimate. Okay? So that's the reason that you can use the second derivative to determine whether the tangent lines provide an over or an underestimate. But we're doing something a little different with this. That was just an aside. Okay, we've got this concave down, concave up business. Go and recall the actual question. In the first and second quadrants, the relation is concave down. And in the third and fourth, it is concave up. So I want to rephrase that as concave down means that we should be able to show y double prime is negative. Okay, and then concave up, we should be able to show that in quadrants 3 and 4, y double prime will be positive. Well, it looks like we're going to have to find a formula for the second derivative, as unfortunate as that is. We will grab this. And guess what the second derivative is? It is the derivative of the derivative. So if we want to find the second derivative, we begin with the equation for the first derivative and we differentiate both sides. So just to write that specifically, you differentiate both sides, and that gets you y prime on the left. On the right is where all the hard work happens, but we'll do it. So, ready? This is going to be wild. We differentiate and we get y double prime. Yay! But then on the right, we've got quotient rule. Now, it may have been a while since you applied this, but quotient rule says that the derivative of u over v, if you use u to mean the top and v to mean the bottom, it's u prime v minus v prime u all over v squared. So it's top prime bottom minus bottom prime top over bottom squared. Let's apply that to this. The top is our u and the bottom is our v. The derivative of the top. Let's think of the top as negative 9x. So I'll make the minus sign live on the top of the function. Maybe just make that a little more explicit right there. So the top I'll think of as negative 9x and the bottom will be positive 4y. Derivative of negative 9x is negative 9. The bottom is 4y minus, so at this point I'm here in the quotient rule. Now derivative of the bottom, it's going to be 4y prime. And then times negative 9x, that's the top. The whole thing goes over the bottom squared, which is 16y squared. We obviously need to simplify. Negative 36y. This double negative becomes a positive. So this will be plus, and then 4 times 9 is 36. Then x times y prime. Look, you've got the variable of x here and the variable of y prime here. Now, it's not okay to include y prime in the formula for the second derivative. So what I'm going to do is this. I'm going to write it for now, but this, that is sad face. We can't have that. So what you do is replace with the formula for y prime, which you already got in the first part of the question. Okay, so remember that our y prime we know to be negative 9x over 4y. I'll get rid of these u's and v's because now they're cluttering it up. So that y prime needs to get replaced because our formula can't involve anything other than just x's and y's. Do some rapid fire algebra. 36x times negative 9x over 4y all over 16y squared. Blah, 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 blah. We've got 36 and 4 that cancel down to, what is that? 9 and 1. And then negative 36y minus 81, that's 9 times 9, x squared over y, all over the same 16y squared from before. Get common denominators on the top. So this needs to go over y. That will be negative 36y squared minus 81x squared. Both of those over the single y, that's just this one, but then also over 16y squared. Now, you may immediately jump to this, which is fine. Negative 36y squared minus 81x squared all over 16y cubed. If your algebra is a little faster than this, then I'm trying to do this so that everybody can follow along. You can skip a few steps ahead if that's fine. So the assertion of the problem was that this was concave down in quadrants 1 and 2 and concave up in quadrants 3 and 4. I want you to look at the top of this fraction. This is the second derivative, by the way. We found it. Now we need to use it to determine the concavity. So look at the top of the fraction. The top is a square for the y and a square for the x. Now, what we know about this, pay attention closely. This y squared is always a positive number because a square is always positive. X squared is also always a positive number. That means that negative 36y squared will always be negative because it's a negative times a positive. And then you're subtracting a number that you know to be positive. So you've got a negative minus a positive. A negative minus a positive is something that is guaranteed to be negative, right? Because you can't make a number positive if it starts out negative and then you subtract something. Well, that only makes it more negative. So the top is always negative. That means that the positivity or negativity of the second derivative will depend entirely on the bottom of the fraction. The bottom is positive if y is positive, but it's negative if y is negative. Now think about what unifies the first and second quadrants. Quadrants 1 and 2, that's here and here, those are unified by the fact that y is positive in those quadrants, whereas quadrants 3 and 4 are unified by the fact that y is negative in those quadrants. These fit together exactly. So the second derivative is positive if y is positive. Oh, you mean positive if you're in quadrants 1 or 2, right? The bottom is negative if y is negative. So that means if you're in quadrants 3 or 4. So in quadrants 1 and 2, you've got a negative. Remember that the top is always negative, divided by a positive. That means you've got a negative second derivative in quadrants 1 and 2. So up here in this area, you know for a fact that you've got a second derivative that is negative. Well, that means you're concave down, right? Oh, it's coming together. And then in quadrants 3 and 4, it's just the same thing, but the other way around. In quadrants 3 and 4, you've got the negative number, which is always on the top, divided by the negative number that we know the bottom to be. So that's a positive number. And so on the bottom, down here, now we know that y double prime is positive, which, no, not down, it's concave up. Bingo! We've shown it. We've shown that the function's concave down everywhere in the first and second quadrants. We've shown that it's concave up everywhere in the third and fourth quadrants. What the heck were we originally trying to answer? Okay, so verify the fact that the relation is concave down in the first and second, concave up in the third and fourth. Good, we did it. Now, finally, number 5, use the concavity of the function combined with the horizontal and vertical tangent lines to show that over the course of quadrants 4 and 1, the relation has tangent lines that cover all possible slopes. So we're going to tie together a bunch of stuff from this problem. We're going to begin by drawing a very basic graph. We're interested in quadrants 1 and 4. So I'm going to give a lot of room on the right. Now think about what we did. It was, what was it? 0, 3 and negative 3? Yeah. So 1, 2, 3, and negative 1, 2, 3. Recall from earlier that at 0, comma, plus or minus 3, we had horizontal tangent lines. And then at 0, comma, plus, sorry, at plus or minus 2, comma, 0, we had vertical tangent lines. So without drawing the relation itself, we know that the tangent lines are going to look like this. They'll be horizontal there, and vertical there. Come on now. There we go. So think about what the tangent lines would look like in between. They go from having a 0 slope right here to having an infinite slope right here. That means that over the course of this, it must have a shape like that, or more accurately like this. See, it's the only way for it to have that behavior. It must have tangent lines that increase because it is concave up in the 4th quadrant. By the time it gets to this point, though, it needs to be entirely vertical. So in quadrant 4, it has all possible positive tangent line slopes. We wanted to show that in quadrants 4 and 1, it had all possible tangent line slopes, period. In quadrant 4, it has all possible positive tangent line slopes. You probably know what's coming. In quadrant 1, it goes from having a horizontal tangent line here to having a vertical tangent line there, but now it does it like in reverse. So it must have this sort of shape in the 1st quadrant. And that would mean lots of these sorts of tangent lines. That's messy. There. These sorts of tangent lines. So guess what? In quadrant 1, it has all possible. What sorts of tangent lines are these? These ones were the positive ones in quadrant 4. And they cover all possible positive slopes starting from 0 all the way to positive infinity. Now you've got these negative slopes up here, and they go from 0 at the top all the way down to negative infinity. Now, it's sort of a weird thought exercise to think that a slope of a line that's negative infinity and positive infinity, they're like the same. That's weird, but it is one of the conclusions here. So in quadrant 1, it has all possible negative slopes. It's the concavity of the function, because you know that it starts at 0 and goes to infinity, and it's increasing the entire time. Well, that means that it must cover all possible positive numbers. Whereas keep going along here, we can even go in the opposite direction. Go from here, where it has no, actually that would be confusing. Let's start from here. It starts from 0, and then it goes from left to right. It traces through from 0 down to negative infinity, and it's concave down the whole time. So these must cover all possible negative slopes. This relation is an ellipse. It's a widened out circle that you covered in pre-calc if you took a good pre-calc class, but we're looking only at this half of it. There you have it. You can answer lots of interesting geometric questions with the implicit differentiation, the first derivative, and the second derivative.